In today's lesson, you will learn the rules of exponents, and you will learn to use the rules of exponents to simplify expressions involving powers. You should already know the definition of an exponent and be able to simplify numerical expressions involving positive integral exponents, the zero exponent, and negative integral exponents. In other words, you should know that a positive exponent tells you the number of times to use a base as a factor. A zero exponent for any base will be 1, and that a negative exponent tells you to take the reciprocal of the base. As you go through today's lesson, be sure to take careful notes. I give you several starred rules. Be sure you memorize those starred rules and put the rules on your study sheet. You'll be using the starred rules, the rules of exponents, for as long as you take mathematics. Let's start with an example. Let's simplify 3x squared times 2x cubed. So we want to simplify 3x squared times 2x cubed. By the associative and the commutative properties, I can regroup so that my numbers are grouped together and my powers are grouped together. Doing that, I have 3 times 2 times x squared times x cubed. Now I can multiply my numbers as always. 3 times 2 is 6, and I can analyze what my powers mean. Now x squared means x is used as a factor 2 times. So the x squared means x used as a factor 2 times. The x cubed means x used as a factor 3 times. So x used as a factor 2 times, x used as a factor 3 times. Now notice in all, x is used as a factor 1, 2, 3, 4, 5 times. So I can write it as 6x to the 5th. Now that strategy works fine as far as writing out what x squared means and what x cubed means, as long as you have small exponents. But what happens if I say simplify 8x to the 196 times x to the 321? Well, we could do it the same way. I can write down the 8, then I can write x as a factor 196 times. I can write x as a factor 321 times. Then I can count the number of times that x has been used as a factor. Once the workload gets this heavy, most people want to know an easier way. That's where your rules come in. The rules will give us an easier way of doing it. Now before I give you the rule, let's try to see what it's going to be and how it works. Now notice here, this tells me to use x as a factor 2 times. This tells me to use x as a factor 3 times. Well, if I use x as a factor 2 times, and then I use x as a factor 3 more times, I've used x as a factor 2 plus 3 or 5 times. That indicates that to multiply powers having the same base, I would keep the base x, but I would add the exponents. If I use it 2 times and then use it 3 more times, I've used it in all 5 times. In fact, that is your rule of exponents that I'm going to give you now. Now notice this has been starred, so this is something that you will have to know. To multiply powers having the same base, keep the base and add the exponents. Writing it symbols, I can say x to the a times x to the b is x to the a plus b. In other words, to multiply powers having the same base, x, you keep the base and you add the exponents. Exponent a plus exponent b. Now we can go back and do the example that we had previously very easily. We have 8x to the 196 times x to the 321. Now I can regroup So the 8 is by itself, and the x to the 196 and the x to the 321 are grouped together. Now my rule says to multiply powers having the same base, keep the base and add the exponents. So I can write down the 8, I can keep the base x, and I can add the exponents on the x. So I'm adding the exponent 196 to the exponent 321. Taking the calculator and adding 196 plus 321, we get 517. So the answer is 8x to 517. So using the rule, this problem was fairly simple. Using the definition of exponent, as we did the first example, it takes forever. Now that we have the rule applies to negative numbers, and it also applies to literal exponents. So we can do a lot of things now that we had not previously been able to. That's another advantage of a rule. It will allow us to expand what we can do. Let's look at another example. Let's simplify 2x to the negative 4 times 5x to the 12th. Notice I have the negative exponent. Well, what I want to do first is use the associative and the commutative laws to regroup and reorder. I want to group my 2 and the 5 together and group the powers of x together. So I can write it as 2 times 5 times x to the negative 4 times x to the 12th. I can multiply 2 times 5 and get 10, and I can remember the rule. To multiply powers having the same base x, I keep the base and add the exponents. So I add the negative 4 plus 12. So the answer would be 10x to the 8. Negative 4 plus 12 is 8. Let's look at another example. Let's simplify x squared y to the negative 3 times x to the negative 8 y. What I want to do is to use the associative and the commutative property to change the order and grouping so that like bases are grouped together. So I'm going to group x squared and x to the negative 8 together. I'm going to group y to the negative 3 and y together. Now that's by the associative and commutative laws of multiplication. So I simply do the grouping. Now once I group, I need to know my rule. To multiply powers having the same base, I keep the base and add the exponents. Now notice one thing. Here I've got y. Y doesn't have an exponent on it. The exponent's understood to be 1, so I write it here as y to the first. Keeping the base x and adding the exponents, I get x to the 2 plus the negative 8, and then keeping the exponent y and adding the exponents, I get y to the negative 3 plus 1. So notice multiply powers having the same base, keep the base and add the exponents. And now simply finishing it, we have 2 plus the negative 8 is negative 6, and negative 3 plus 1 is negative 2. Now remember from yesterday's lesson, a negative exponent tells you to take the reciprocal of the base. So x to the negative 6 is 1 over x to the 6th, y to the negative 2 is 1 over y squared. Now multiplying, I finally get the answer as 1 over x to the 6th y squared. 1 times 1 is 1, x to the 6 times y squared is x to the 6th y squared. Since these bases are different, I cannot simplify further. Let's look at an example in which we have literal exponents. Still works the same way.